Hello, everyone. My name is Scott Eisele, and thank you for joining me for this presentation of Modicum, Mechanisms for Outsourcing Computation via a Decentralized Market. First, the outline. I'll present the introduction and overview, identify the research gaps, introduce our platform, provide an operational analysis of the protocol we use, evaluate and understand the overhead that is caused by the platform, and provide conclusions and future work. Smart devices are all around us, and they enable many new and exciting applications, including in the fields of transportation, energy, and many others. For instance, our lab has done work in the domain of transportation to improve transit operations. These require efficient data analysis and inference. However, these applications generate a lot of data, and the cloud has limited bandwidth, so using the cloud to implement some of these applications would be impractical. We can improve efficiency by bringing the computation power of the cloud closer to where the data is being generated in the form of fog and edge computing. The problem with fog and edge computing is that edge devices can be owned or operated by multiple stakeholders, which have differing objectives. Additionally, for fog computing, most solutions assume resources are available from micro data centers or internet nodes, such as routers, gateways, or switches that are augmented with computational power. These solutions do not take advantage of the vast potential of idle compute devices that are already deployed and would be much less expensive to operate than maintaining full fog node deployments. So if we want to access these underutilized resources, how do we get access to them if they're not owned or organized by a single centralized micro data center? One effort to accomplish this is volunteer computing, and that is a step in the right direction. They were able to convince people to volunteer their compute resources to do complex scientific computations. However, they suffered from low participation, and as part of their platform, they include a leaderboard to track how many computations each of the volunteers contribute, and some volunteers falsely claim to perform work in order to head up the leaderboards. So even with just limited incentives of topping the leaderboards, that was enough incentive to convince some participants to not do the work that they were assigned. So our hypothesis is that an open market is required in order to increase participation. However, providing incentives to encourage participation also introduces a motivation to attempt to game the system, as we already saw in the case of the volunteer computing. So we need to present misbehavior and hold agents accountable. Essentially, we need mechanisms for consensus. So the key research questions we're focused on is, assuming rational agents, how can a market be constructed which minimizes verification overhead while providing acceptable correctness guarantees? Also, what is the appropriate market architecture? Should it be decentralized or centralized? Creating a decentralized market for a compute sharing economy is compelling because it improves resilience and encourages competition. So that is the direction that we took with this work. So the state of the art for decentralized markets with multiple stakeholders where they have differing incentives and can't trust each other appears in distributed ledgers, for example, Bitcoin and Ethereum. In these platforms, there's an immutable append-only ledger that records all the transactions and communications between the various stakeholders. And each stakeholder has a copy of the ledger so they can ensure that all the transactions made are correct. This provides consensus on the state of the market in our context. And so Bitcoin provides this decentralized market for financial transactions, and in Ethereum extends those capabilities by enabling computations on the data that is stored in the smart contract, that is stored in the distributed ledger in the form of a smart contract. So the result is an open, immutable, auditable, censorship-resistant transaction platform that can provide trustless computations. However, there are some gaps. We cannot directly use these smart contracts to outsource the computation because they have limited computational power and it's expensive since all the nodes in the network have to all the nodes that are participating in the security of the network have to replicate that computation. So the key is to integrate the blockchain as the management of them for the management of the market and to enable fair computation rather than performing the computations directly using the distributed ledger and smart contracts. Essentially outsourcing or offloading the computation off the chain and only handling management on the chain. An example of this type of solution is called Troutman, a blockchain-based platform for outsourcing computations. However, in that example, it was still inefficient for complex tasks. They always verified every computation, which increases the overall costs, and they lacked formal protocol analysis. It's also critical to understand the impact of the various system hyperparameters and how we can tune the systems to provide security guarantees. So now we'll present our contribution modicum. To begin with, the market architecture. It's fairly straightforward. The job creators and the resource providers call smart contract functions, enabling them to submit offers which are stored in the distributed ledger. As mentioned previously, the distributed ledger has limited computational power, so these offers are sent to an off-chain solver, which provides the matching between the offers and submits the matched solutions back to the smart contract market, where the proposed match is validated to ensure that the feasibility constraints are satisfied. This provides a resilient market since the offers are replicated on the ledger and then there are many solvers. So if one solver would fail, there are others which can provide the matching service. Once the match has been made, then ideally you would just be able to transfer the job from the job creator to the resource provider. The resource provider would provide the computation and return the result back, and the job creator would make payment. However, as we mentioned previously, the concern is misbehavior. The data transfer could fail, or one of the actors could be malicious. The resource provider could refuse to do the computation, or the job creator could refuse to pay for the computation. So we need to be able to hold them accountable. We do this by adding directories and mediators to the architecture and enabling the ability to store deposits in the smart contract. So to enable the computation, we first require the job creator and the resource provider to commit deposits in the smart contract that can be used to enforce punishments if they misbehave. Then the job creator transfers the job via a directory, a secure data store, to the resource provider. The resource provider provides the computation and transfers the results back. At this point, the job creator has several choices. And since we want to limit the overhead of the platform, we elected to have the job creator verify the result with some probability. It could verify every task, but then there would be no point in outsourcing. And we must verify some tasks, otherwise the resource provider would have no inclination to provide the computation. So the job creator verifies with some probability P. If it does not verify, then it immediately pays the resource provider. If it verifies and the result is correct, it should pay the resource provider. And if it verifies and the result is incorrect, then it should request mediation by rejecting the result and notifying the mediator through the smart contract communication fabric. After rejecting a result, the mediator obtains the job and computes the results and then provides an outcome. When this outcome is released via a smart function call to the smart contract, the funds are released depending on the outcome chosen by the mediator. So either the job creator is fined and the resource provider is paid, or the resource provider is fined and the job creator is compensated for the loss of utility because the job that it was expecting to get computed did not get computed. This provides an efficient verification by minimizing the repeated executions and minimizing the mediator intervention, since the mediator is only called in the case of a dispute. So the smart contract is central and pivotal to the operation of this market. So we're going to quickly review the smart contract functions, as well as on the right, the finite state machine of a job and how it progresses through the market. So this set of functions is essentially to initialize the market. These have to occur once at the beginning before any of the real market activity can happen. After this, the job creators and resource providers can post their offers. And once both have posted at this point, they can still cancel these job offers after initially posting them. But eventually, once a job offer and a resource offer have been posted, they can be matched. And once they've been matched, they can no longer cancel their offers. So the solver posts the match, and then the resource provider fetches the result and performs the computation and then posts the result for verification. The job creator fetches the result and can either reject it or accept it. If it accepts it, the match is immediately closed. If it rejects it, the job is sent for mediation, and then the mediation posts the mediation result, which also closes the match and awards compensation according to the outcome. We also include timeouts. So if there is a match that is made and the resource provider does not provide a result within an expected time frame, then the match is able to close, the resource provider is fined, and the system is able to continue, and the job creator can re-execute or resubmit the offer if that job still needs to be executed. To go into a little bit more detail on the off-chain solvers, essentially the job creators and resource providers submit their offers to the solver, and in this work we used a maximum bipartite matching algorithm, which is subject to the feasibility constraints in the lower right, which ensure that the resource provider can satisfy the requirements of the job. Because of this, the nature of the solver being separate from the market as its own entity, each solver is free to use any allocation algorithm. And then the smart contract will verify that that allocation is feasible. So this gives us resilience and flexibility to use various algorithms for finding efficient allocations of resources. So now that we've looked at the protocol for the platform, we need to determine whether it will actually provide the security that we need in order to be able to trust it to outsource our computations. So the verification strategy, the role of the mediators, relies on repeated execution. The ideal behavior is essentially that a task given to the resource provider provides a result, and that same task given to mediator provides the same result. But it's possible that if the task can determine where it's running, whether it's on the resource provider or whether it's running on the mediator, that the result could be slightly different. And that the job creator could then extract the meaningful result from what was provided by the resource provider and have a way that it could convince the mediator that the resource provider submitted an incorrect result. In this way, it could avoid paying the resource provider for the service. So for this reason, the resource provider must execute the jobs in an isolated environment. However, we considered if the job creator can still construct jobs that will allow it to get work done for free. And there is a way to accomplish this through non-deterministic tasks with non-deterministic results. If a task, when it's executed, can produce two different results, one with probability PA and the other result with probability 1 minus PA, one of these can be considered kind of normal, as in it will look normal to the mediator, and the other can be considered anomalous. So it will look anomalous to the mediator. And the reason for this is because if the mediator were to run that task, the more probable task, or the more probable result will happen with result PA, and the less probable result will happen with probability 1 minus PA. And so if the mediator performs many computations, then it's possible that it will never see the result with the B modification. It will only see the result plus the A modification. So if the resource provider submitted a result with the B modification, then the mediator will not detect that cheating. And so this cheat can occur with probability 1 minus PA times PA to the N, where N is the number of times the mediator repeats that computation. So the question we ask is, can we bound the amount of cheating that the job creator can accomplish using the operational parameters of the platform. So first, what are the operational parameters of the system? These are the amount of job creator and resource provider deposits, as well as compensation for the faulty party, as well as the number of times mediator verifies. So we set these parameters as seen here below, and then we created an extensive form game between the actors of the platform. And using these utility functions, we're able to determine what the behavior of the agents will be based on these outcomes. And so we can set the parameters to drive agent behavior to a particular outcome. So for example, if the participants choose to if the resource provider chooses to execute, the job creator chooses to verify, and the result is an anomalous result, then one of outcome 6 or outcome 7 will happen. And if outcome 6 happens, this is the outcome, and we show the rewards for this particular outcome. So using these outcomes, we can construct a decision table where we can compute the utility for each possible pairing of decisions. So for the execute verify combination, we take the probability of outcome 6 plus the probability of outcome 7, and we get the utility for the execute verify kind of decision pair. And then to bound the decisions of the job creator on PA, we can take the derivative of its complete utility function according to, or with respect to PA, and solve and simplify and solve for the system parameters n and theta. So the number of times the mediator needs to compute and what the fine or the penalty rate should be. So since we're only interested in a bound, we can take this optimization and simplify it using the worst case parameters and set our two system parameters and solve for the probability of the job creator successfully cheating on a particular task. And so we see that as n increases, the probability of a task being accepted or being normal goes up. And so if we set n equal to 2 and we set the penalty rate equal to 50, then regardless of the other values in the system, a rational job creator will choose to have a very low rate of the task outputting the result B. And so 99% of the time it will output result A. And so this limits the amount of cheating that the job creator can perform. So understanding the overhead of the platform, the nominal execution of modicum adds about a minute to the total job latency because of all the smart contract function calls and waiting for them to return results. And so that impacts kind of the end-to-end latency of a particular task, and then the actual runtime is only modified by 4%, and then the memory consumption is modified by 3%. This was running jobs from the Parsec benchmarking suite, specifically the body tracking application. And so we also wanted to understand the costs of running modicum if we were to use the public Ethereum blockchain. And using the estimated gas costs of each of the functions, we were able to compute the nominal cost for executing a task. And this converts to about 17 cents in transaction fees for calling these functions. And this could be improved with more efficient function calls probably. Anyway, comparing this cost to the cost of running on AWS for a 512 MB RAM instance, we would have to run for about 5.6 hours in order to reach that same level of cost. So in its current form, the modicum platform is only really feasible for very long running tasks, so over 6 hours essentially. But if we look at the electricity costs of running on an edge device, such as a BeagleBone Black, which has 512 megabytes of RAM, the electricity costs are not even are $0.0016. So this is 100 times less than the costs in AWS. So this illustrates the potential for such transaction systems. But again, as we mentioned, using the public Ethereum blockchain is only feasible for very long tasks. But there is a space in between for a platform of this nature. So in conclusion, this platform deters participants from misbehaving by resolving disputes via dedicated mediators and imposing enforceable fines through a smart contract. And this is possible because we recognize that results do not need to be globally accepted, and that convincing the job creator will often be sufficient. The downside is, due to the limitations of the public Ethereum blockchain, our platform is only suitable for long-running tasks. But there is space between the cost of electricity and AWS for a platform of this nature. We just need a less expensive platform. And for that reason, future work is looking into other platforms that support smart contracts as well as leveraging improvements to Ethereum. And so this work is a first step towards a market for general edge computing applications. And as part of that, we're looking into converting this from batch processing to stream processing and the other alterations that would be necessary to ensure correct computations. The source code for this work is available online. And are there any questions? Thank you.